going to talk about borrowing, how we can model borrowing in Scala from Rust. I'm Leo Osvald. A PhD candidate at Purdue University. The co-author here is T.R. Krumpf, my advisor. Today I'm going to talk about how to model borrowing from Rust in Scala. So before we dive into that topic, let's consider some danger of mutability. A program that concurrently accesses the same memory is prone to data races unless it makes no write, or it makes a single write provided that accesses are all atomic. So here we see an example that this is a problem even in sequential problems. We create a mutable list containing a single natural number, number 1, and we keep iterating over it while at the same time appending the next natural number to it. And
can you speak closer?
This in Scala has unexpected results, so we would expect that it prints either 1 if the newly appended elements are considered during traversal, or that it would print 1 through 10 if they're ignored, but what happens is it prints just 1 and 2. In C, if this was C, that would be a program crash due to a dangling pointer, and Java would certainly throw an exception, concurrent modification exception. So some solutions to this problem are extreme ones, like Haskell, where there is no mutability, everything is purely functional. No external mutability, to be precise, so there is st-monad. And then in R does copy and write, which is whenever you want to mutate something, before the mutation it will be copied and unshared. These things have been, in the past, these things have been studied theoretically and in Scala to some extent, but Rust is the first language that seems to make this practical. It's actually accepted by not just scientists but also developers, and it's gaining traction even though the ownership type systems have been hard before. So the question is there anything we can learn from Rust? Let's see how its borrow checker works. So in Rust, the borrow checker enforces 2 rules. One is you can have multiple immutable references, but if you have a mutable reference, then you can have no other references to the same memory. There is also a concept called reborrowing, where you can temporarily alias something, but only for duration of a function call. So that's safe because the reference at the call site is not live until the function returns. Here is an example. We create a mutable reference to memory containing integer 5. Then we create another reference to the same memory, this time a mutable one, through which we increase that number, and then we print it. This does not type check in Rust. It says that we have already borrowed X mutably, so we can no longer borrow it mutably when we print it. It's hard to tell that the line at fault is actually the second one here, but if we take a desugared version, then we'll see that that line causes an implicit scope to be open, which ends at the end. So in this new scope, indeed, there is a shared mutability. There is both Y and X. Here in the second line borrows X immutably, and the printing borrows it immutably. So that's a violation of those rules. As we can see, Rust type system is context sensitive. So if you want to do something similar in Scala, it would be very hard because of this mismatch of flow sensitivity and flow sensitive, flow insensitive typing rules. But why is this important? Because Scala, there is a recent library in Scala native, it's basically a framework for external memory management. So is there a way to bring some of that behavior to Scala? So if we try just to translate typing rules, the Scala type system is already complex. So if we add this whole new other dimension to it, it will just multiply the complexity. So how can we express this borrowing and alias control in Scala in a similar but simpler, using a similar but simpler mechanism? The answer is actually yes, we can do it, but we just need to give a little bit up on expressibility, so we're not going to model ownership transfer or full-blown ownership system, and we're not worry about continuation passing style, which can be easily eliminated through a compiler plugin. You can take a look at the CFP paper where there is a mechanical elimination of monetic style. So our key idea is to basically transform this this type-sensitive code, Rust code here, to Scala code, which is type-insensitive. We are going to do this by introducing, whenever we have let y equals mut x, we are going to create a new scope through a closure that introduces parameter y that binds some initial value x. Here is what we want to do. So here are type checking rules that we want to enforce. If we bind something as immutable, then we cannot bind it again as mutable, or vice versa. Then we can, but if we bind it again immutable, that's okay. We also do not support assignments on immutable; they cannot be reassigned. Here, there is a similar case where we first introduce something as mutable, then if we try to introduce as immutable, that's again violation of the second rule in the reverse direction, and also if we try to rebind it again as mutable, it would be shared aliasing. But we support assignments of that value on the immutable variables. Another thing, we should enforce lexical scoping so that we cannot return a variable from a scope, or we cannot use it outside the scope. So the intuition here is we are going to use second-class values which exactly enforce those lexical scoping. Because the property for borrowed reference is essentially the same as for also holds for second-class values. So our design is, we have two levels. One is library level that is going to enforce those three rules mostly, and there is a meta level which will prevent some workarounds. So in the library level design, the first thing we have is a wrapper, variable wrapper that has two type parameters, the type of underlying memory T and the type of access A, which is either immutable or mutable. The getter is always enabled and setter is only enabled if access is mutable. Second, we have implicit conversion. We give high priority for conversion to immutable because immutable is less restrictive. And in both cases, we can convert, we can create basically a wrapper variable out of a value. So now before we talk about bind function, let's revisit our second-class value that we introduced in UPSLA paper last year. Their key properties are first, they cannot be stored in a var in Scala, basically mutable variable. They cannot be returned from a function, and second-class variables cannot be accessed as free variables from a closure, from a first-class closure. And also, there is a property, since they are more restrictive, you cannot coerce them to first class, while you could coerce first class to second class. Now, it's obvious that we can, so basically, from these properties, it's obvious that they actually, if we make those variable wrapper second class, then we'll enforce their lexical scoping. So here is the signature of bind mute. We can see that The trick is here that we introduce the variable as second class. That way it cannot escape, it cannot be returned from that block. But then when we have an initial value, we require it to be first class. So this means once you introduce something as second class, you can no longer bind it in an inner scope to another bind thing as mutable, because you cannot give up second classiness. That would not type check. And the subtlety here is that there is this closure here is also second class, in order to circumvent this restriction that we cannot access second class values as free variables in a first class closure. So that allows nesting. Here's how it works. So you can nest and access the outer one, but if you try to bind it as a initial value, then it will not type check. You cannot convert second class to first class. For immutable, the only difference is that we allow the initial value to be second class. That way you could bind something that is introduced as immutable again. But because of this phantom type immutable here, then we cannot treat mutable as immutable. Next we come to meta level design. To remind you that we'll take care of some workarounds, prevent them. The first workaround we should worry about, what if somebody uses ref.value like through a getter, and then that will be converted, that may be converted through implicit conversion to a wrapper. So that's a problem. To prevent that, we have two wrapper macros, let and let mute, which are performing syntactic inspection of initial value to see whether there are an expression involving ref.value, some wrapper.value. Basically, they must be either, those initial values must be either R values or like literals or even expressions, or another variable wrappers. Another workaround is what if we is storing basically a ref.value to some other variable and then putting that variable or expression containing that variable as initial value. So again, in this case it could be an R value, so we need additional work. So here we prevent any assignment of a ref.value or an expression containing that, or even declarations that contain this as initial value. And now we come to the key concept of our work, which is borrowing, how to model borrowing. As I said earlier, because of the similarity of second class value and borrowed references, we can just make the references that we expect to be borrowed. We just make those parameters second class, these local annotations. And we also need to use those wrapper variables. And here is then how we could have a function that borrows two arguments. And we could similarly have, we also support this form here, which Rust does not. But if you just inline this function, then you would have something like that. If you want to temporarily alias, then you should mark it as second class. We could again prevent this through a macro, but it's not a problem. Now you might be wondering, what if you have a third-party library and then you need to basically transition to this borrowing? How do we gradually introduce borrowing? Because we said we need both wrappers and local annotations. So we could do it in two steps. The first is just add local annotations, and then in the second step, add those wrappers. And in the meantime, so we have this wrapper call where a function may have only local annotation, but does not have to have those variable wrappers. So before you fully refactor your call, you could use that to ease the transition, basically. So here is an example how we could do. Say that we have some code that claims to borrow some two parameters, okay? Arguments to those two parameters. So the first thing we do is we just mark them as local, and then this will ensure, the type checker will now ensure that they are properly borrowed. If they are borrowed, then they cannot be stored. So if we try to store it into a field of a class, then this will not type check, because we said second class values may not be stored into a mutable variable or an object field. And this is indeed makes sense, because suppose that we could store it. So then here is a silly case where we introduce some store that has a field, and we create a string builder. Then we store that string builder into that field, but we leak the alias basically to that string builder by storing it to a field. And now in this scope we would have two references that are mutable. One is the store that has a field, and the second one would be the string builder itself. So at this point where you think that you have the old contents of string builder, something might change it in the meantime. So this is similar to the initial example of traversing and appending. And indeed this is prevented because of our lifetime guarantees of second class values. So in conclusion, I show you how to use second class values in Scala to model key concept of borrowing and alias control in Rust, and how to use macros and basically overload assignment in Scala Virtualized to take care of some workarounds, and how to remain context insensitive. And here the key challenges were how to get, so these are basically our solutions. Here we use second class value to model borrowed references, and we use monadic style to avoid flow insensitivity. Thank you.
So I think the Rust stuff is very interesting, but one take on it I've heard is that the need for this sort of stuff is an indicative sign that mutability is a bad idea, and you add all this complexity to try and manage it, and maybe we should just not have it at all. So what would you say to someone who says just use a pure functional approach?
So I would say that this is somehow more tunable, because you can have you can have restricted mutability, like just temporary for in some function, but and it's still more manageable than unrestricted mutability. But yeah, and I think it already fits well into Scala, because Scala is a multi-paradigm language where you can use even some stuff from Java. So for more practical adoption, I think it's important to allow some sort of mutability.
So we're stuck with mutability.
Yeah.
That's what we're saying. Okay. Yeah.
Yeah, so I have a question about the leaking references. So couldn't you have one of these var wrappers and store an object that has, that's mutable, and then well, how do you prevent sort of these indirect leaks through objects that have transitively references to other mutable things?
How do you prevent those? You cannot prevent them, and you need to fully replace all the references with wrappers, similar in Rust. In Rust, you really need to introduce everything scope by scope. in Rust there is also like some static lifetime. We do not support that, but it's something in here. If you want to work around it, you can still use like regular functions that do not have local annotation on parameters, and that way this can leak stuff. But again, you cannot leak out of some wrapper, because once you have a wrapper, then you cannot basically leak dot value out of a wrapper. And we could imagine having something like, so this work was mostly concerning how to model this alias control and borrowing, but we could go further and model some sort of ownership by introducing a wrapper, something like with dereferenced, that takes this value and introduces a scope where this value is dereferenced, but it's second class, so it cannot escape. But this would be more restrictive, because then you would not be able to do anything with it. The whole code would need to be almost the same as Rust code. This is some step that you can take further, but we didn't, because it would be harder to adapt and make it practical.
Okay, yeah. I mean, in this, in my paper on La Casa last year, Uppsala, basically the idea was that you can have, you can do a sanity check on a class declaration, right? Which is sort of one bit, like, does it conform to this object capability model or not? And if it does, it's you have some additional safety guarantees, basically. I mean, you could probably use something like that as well.
Yeah, that's very nice. We're actually considering extending this with some of the ideas of La Casa paper.
Right.
That's the future direction.
Okay, cool. Thanks.
Everybody's ready for lunch, so
Mm.